Hi, my name's Fred, and I'm a research scientist at Apple. Today I'm going to be talking to you about our work on Talaria, an interactive visualization system that we've built to help machine learning practitioners optimize their models for efficient inference. This is actually the second paper in a pair of papers we have at CHI this year, all about model compression in practice. The first is an interview study we ran with 30 experts at Apple to detail some of the challenges and opportunities that practitioners face when moving models on device, such as phones, tablets, and computers. In this work, we're going to detail a tool that we've built to try and address some of those challenges that we learned in the interview study. So I quickly just want to highlight the benefits of efficient and on-device machine learning. Why should you care? Well, first, it protects users' privacy, so your data doesn't have to leave your device whenever you want to run a prediction or inference on it. And this also enables new user experiences that otherwise couldn't exist. For example, if you have to run a prediction, say 30 or 60 times a second in some sort of camera application. We also don't have to rely on network access because our model can run offline directly on our device. And it has some positive environmental impact as well when we don't have to rely on a large server that runs elsewhere. But there's some big challenges with this work too, such as how do we go about optimizing and shrinking models in order to fit them on these devices? And how do we go about picking and choosing from all the various optimization options that exist? And more importantly, how do we integrate this in efficient ML practitioner workflows? So all this work leads up to this tool that we built called Talaria that helps practitioners interactively optimize their models for efficient inference. And Talaria has two main views, a table on the left and an interactive graph on the right. And we're going to spend the next few minutes sort of giving you the design, justification, and context that'll ultimately end in a demo of this system at the end of the talk. So to get started, how do we go about designing Talaria? Well, we did some formative research, including two big studies. The first was a need-finding survey with 12 practitioner responses that were all experts in both efficient ML and hardware optimization. And these people had 75 years of experience between them, so we were pretty confident in what they thought about the work. And then after that, we ran a participatory design session where we had built low-fidelity prototypes with practitioners' own data over the course of about 2 months. And all these various prototypes together ended up being the first version of Talaria. So the key design challenges that it comes with efficient machine learning work from both these studies that we ran, the first is that practitioners have to inspect large amounts of data, both geometrically and analytically, and they want tools to be able to support looking at their data in various ways and summarizing it too. Second, it can be hard to find what they call model bottlenecks. These are hardware operations that run on a particular device that take up a majority of the compute. And so you can actually if you can find these particular bottlenecks, you can compress them and leave the remaining of your model intact. There's many different optimization options to choose from, and so practitioners have preferences over which ones they'd like. And it also requires multiple practitioners. This is a highly interdisciplinary type of work where you need hardware engineers, machine learning practitioners, in order to design the best model possible. And lastly, applying these optimizations back in one's code can take a lot of time. Right? You have to find exactly which parts of your code generated the various operations that are running on a hardware set. And so in Talaria, we go about solving each one of these 5 challenges. So first, in order to tackle this large amount of data, we're able to summarize and load tens of thousands of hardware operations that are running on a device and visualize those both as a table and an interactive graph that are synced. We also can then use some nice encodings on top of this graph in order to find the nodes that are particularly computationally expensive. We also implement a variety of popular model compression techniques, and we present those in our tool so that practitioners can choose from them. We also support some GitHub-inspired analysis and saving features where practitioners can optimize a model, save it, fork it, and then send it to their colleagues in order to pick up where they left off. And lastly, we have a really neat feature called code mapping, where we can directly go back and forth between the operations that run on hardware and the source code that generated those operations. So the last thing I want to highlight is just give you a sense of the type of model compression techniques that exist that Talaria supports. So with compression, the goal here is to minimize a model's computational resources without significantly modifying its performance. So some popular techniques include quantization, where our models are stored as floating point numbers, and instead we can cast them to a lower precision format such as integers. It's a great way to save space on a model. We can also prune or sparsify a model, which is to remove unimportant weights that don't contribute much to the prediction. Or even use something called palletization, where instead of casting from floats to ints, we can then reduce all of our floating point numbers to some predefined set of values. So we only are dealing with some sort of reduced discrete set, kind of like a dictionary lookup with our model. And we can apply these techniques in two sort of modes. The first is what we call model-wide optimization, where you sort of just bluntly apply one of these techniques to the entire model. Or with Talaria, we can do target optimization, where we can find only a particular set of operations that we can apply our compressions to. So let's now look at a demo of our system in practice. We're going to be running Talaria on a UNet model that's been loaded onto a device that's running on hardware. So to start, let's take a look at the interface. On the left, we have this table where all the rows of the table are the hardware operations of our model. And the right, we have that same model visualized as the actual graph with the edges of compute. In the top, we have some top-level metrics, such as the memory power and runtime of a model in milliwatts and milliseconds. And we can just go about exploring this model. So we have a little mini map, so you can zoom in and get your position within the model, and you can select various nodes. And you'll see a really important feature is that everything is synced together. So when you click on a row in the table or a node in the graph, it's zoomed or scrolled so that you can keep track of the exact operations you're exploring. There's other selection features, such as selecting multiple nodes in the graph, and that'll filter in the table on the left. Or for example, we can filter or sort the table on the left to look at the corresponding change on the right. For example, here we can find all the pooling operations of this model. Turns out there's only 5 of them. Or instead, we can actually just look at all the convolution operations. These are ones that we're probably more interested in optimizing. We can then filter them by ones that take a longer runtime than only 1 millisecond or so. And it looks like there's really not that many. Maybe only a dozen or so of these metrics, or operations rather, are taking longer than a millisecond to run. So if we sort our table by the runtime, we see that distribution shape in the little bar chart there. And so what we can actually do is color the graph by any one of these metrics, such as the runtime here. And sure enough, we found a couple of operations that are taking up a majority of the computational time. And so these are these bottlenecks that we're going to want to optimize. So now let's take a look at these interactive optimization options. We're going to click the Optimize button, and we get presented with a list of all the different options and combinations of hyperparameters of quantization, palletization, and sparsity. We're going to filter the input, output, and kernel format just to integer 8s, because we just want to quantize this particular operation. And so when we pick that, we see that just by optimizing that one particular node, we've actually reduced the memory power of our model by 43% and the runtime by 17%. These are huge gains by just finding that one sort of needle in the haystack. Let's do that one more time. We're going to find another operation. We're going to once again filter, and we're going to quantize the input, output, and kernel format to in8s. We're going to select our option, and now we've reduced our model even further. Just by those couple of tweaks, we've brought the memory power down by 60% and the runtime by 22%. So this is a great analysis, and I want to save this to come back to it later. So I'm going to click the Save button. It's going to prompt me for a name, so I'm going to name this analysis so that I can revisit it later and maybe show someone else on my team. But remember, I also said that Talaria supports both targeted and model-wide optimization. So now I'm going to quantize the entire model with this model-wide optimization just as a rough baseline that I want to compare against. And here we see that the memory power has been brought down by 73% and the runtime by 16%. And so the model-wide, by editing everything in the model, isn't that much better than our targeted optimization. I'm going to save this model-wide one just so I can come back to later And in the dropdown here, we can actually toggle between all the saved analyses that we've done. So this is great when you want to compare various compression schemes. So lastly, I want to go about implementing this optimization in my actual code base. So in the code tracking feature, what we're able to do is map the various lines of source code all the way to the nodes running on the hardware. So when we click on that one node we want to optimize, we can find the code snippet and then look at the actual source code and find that exact convolution 2D line function that spawned this operation on the hardware. So direct mapping here. And lastly, we can go about sharing this model. So we can type in someone's email or name. We can send them this URL and they'll pull up the exact model and all of our saved analyses so they can pick up where we left off. So that's a demo of Talaria. And I want to use the remaining time to just highlight a couple of findings we had from various evaluations we ran as we've deployed this system internally. So including a log analysis, usability survey, and interview study. So for this first one in a log analysis, we've deployed Talaria over the course of about 2 years. We've had 800 unique engineers submit 3,600 models to it. And over here on the right, we have the cumulative count of both the users and the models. And one thing I want to highlight is that in the uploaded model chart, we see a lot of these straight vertical segments of the line. And when we went and inspected that data, it turns out that it's a single user who's submitting multiple models at once for a comparison. So they're submitting 3 or 4 models that are subtly different, and they were using Talaria to actually compare various architectures and compression schemes. In our second evaluation, we ran a user survey on the feature usability of our tool. Here we had 26 participants, mostly machine learning engineers, who've been using Talaria for about a year, either weekly or multiple days per week. The full results are in the paper, but the 26 users rated 20 different features of Talaria. We have them grouped in this chart. I just want to highlight 2 findings here. The first is that the core set of features, so this is the table graph and the interactive optimization options. These were rated by far as the most useful, and the actual cross-filtering and syncing feature was rated by all 26 as very useful, so it's great to see. But the sharing and source code mapping features were only discovered or used by about half of our participants. And luckily the ones that did use it, they did enjoy it. But it points to some interesting hypotheses of why these features either weren't discovered or maybe weren't used as much. And we detail some of those hypotheses in the paper. And lastly, I want to highlight this third evaluation where we got qualitative feedback from the power users of our system. So we were able to find the 7 users that had submitted the most models over the course of 2 years, and we asked them about their experience of using the tool and what it was useful for. And while I don't want to go too much into all the results and feedback, I'm going to leave that up to you to check out in the paper. One pull quote I want to highlight is that Talaria was useful because this user can try a couple of optimization options quickly, and it can tell me at a finer level what's going on. This notion of efficient machine learning work being really hard, but Talaria makes it much easier in order to experiment with quickly is a really big boost to productivity when it comes to moving a model on device. So I just want to highlight the importance of this interactive tooling in on-device machine learning work because tools today tend to be homegrown and ad hoc. They're kind of project specific, and it's pretty hard to have one tool fit all various use cases. But tools like Talaria and the ones we think in the future can be much more self-serve and educational to enable anyone to develop deeper intuition about compression. And I'll leave you with this last quote, that tooling is actually education products disguised as software, but better tools make it easy to do correct things and harder to do incorrect things. And this is a great mantra we've used going forward with improving Talaria in the future. So to summarize, in this work, we detail some formative research on model optimization in practice. We contribute an interactive visualization system for efficient machine learning and speeding up inference. And we offer findings from 3 real-world evaluations where we've had hundreds of engineers submit thousands of models over the course of 2 years. And lastly, I'll just mention that once again, this is the second paper in a pair of papers on model compression at CHI. where we detail all the various product design and interactive tooling support that could be useful for this type of work. So thank you so much for listening, and I hope you check out the papers.